Alrighty, good morning, physical science students. Today we begin the last part of Unit 5. We are looking at SPS 2 and SPS 3, bonding and nomenclature. And today we're going to start with a little bit of review from stuff from Unit 5B, some of the skills that we need moving forward. So our goal today is to kind of revisit the organization of the periodic table as well as the charges or the oxidation numbers that the different groups will form. So scientists refer to the charge as an oxidation number. I tend to use both terms interchangeably. But this is the ion, whether it be the positive cation or the negative anion, that our different elements can form. We're also going to look briefly at our Lewis dot model and show how these elements actually form these ions. So, quick review. How do we determine the following for any elements? Remember that our number of protons, we get it by looking at the atomic number. That's the number that's above the symbol on the periodic table. Our number of neutrons, we have to take the mass minus the periodic number. Now, if we're using the mass from the periodic table, we do need to round it to a whole number because you can't have part of a proton or part of a neutron. So it's that rounded mass minus the atomic number to get your neutrons. Your electrons, if the element is neutral, the electrons equal the protons. If they don't, we'll actually look at that example a little bit later, but you have to add or subtract depending on the charge. So if we had a positive cation, we would have to subtract electrons because we lost them. If we had that negative anion, we would have to add electrons because we gained them. My valence electrons, we actually look at that last number of the group number. So group 2 has 2 valence, group 17 has 7 valence. And last but not least, our energy levels. To get that, we look at the period, the row, or how far down into the periodic table a particular element is. Oops. So like for example, sodium, Na, element number 11, is in the third period. It has 1 valence electron, 11 electrons, 11 protons, and I take my 22.99 and divide it and round it to a 23. So 23 minus 11 gives me 12 neutrons. Now recall that with Bohr's model, it is how we can illustrate the position of our subatomic particles. We have inside the nucleus the protons and the neutrons, and then outside of the nucleus we have the different rings illustrating the different energy levels that the electrons can live on. So we put the specific dots on the rings indicating the number of electrons in each energy level. Now remember that there is a pattern to those electrons when we are looking at the electrons. That first ring closest to the nucleus can hold at most 2 electrons. There's only ever going to be 2 dots on that first ring. That second energy level, that second ring, can hold at most 8 electrons, and the third ring can hold at most 18 electrons. Yes, there are more than 3, but we're never going to ask you to draw an element that's bigger than 3. Now we also need to remember where we can find the different elements on the periodic table. Our periodic tables have that bold or that red line separating the big 2 groups of elements, my metals and my nonmetals. With the exception of hydrogen, all of the metals are found to the left of that red line. They are to the left of that staircase. Remember that these bottom 2 rows actually fit in right here, so they are also considered metals. So everything that I'm coloring in blue is considered a metal. Realize that aluminum, even though aluminum touches the stairs in 2 places, it is considered a metal. Any of the others that are on the staircase in 2 spots are considered a metalloid or a semi-metal. To the right of that staircase is where we're going to find our non-metals. So the non-metals are all of the elements to the right of the staircase, including hydrogen. It's the odd one on the table. And my metalloids are the elements who live on the stairs. They have to have two sides that touch the staircase, marking them with little green X's. They are sitting on or just below the staircase. Of course, the exception is our aluminum. So you will need to be able to easily identify looking at an element's position if it's a metal or a non-metal. Our group names. I will be referring to elements by their group names, so you need to make certain you know your group names. Group 1 are your alkali metals. Group 2 are your alkaline earth metals. The spelling is funky. This middle section of the periodic table is my transition metals. Group 13, 14, 15, and 16 are all named after their lead elements. So 13 is boron family, 14 is carbon family, 15 is nitrogen family, 16 is the oxygen family. Those are probably the two that are easiest to remember. Or the four, sorry. Group 17 are my halogens. And last but not least, group 18 is the noble gases. Remember, in terms of our elements, that group 1 and group 17 are the most reactive. We never find them in nature by themselves. They're always in some type of a bond or a compound because they are very, very unstable and they are extremely reactive. My least reactive group is my noble gases, and that's because the vast majority of them are unreactive. That's why we call them the noble gases. They're like the kings and the queens of the table, and they do not interact with any of the other elements. Now, all of the other elements do react to some extent, some more than others. When you start looking at your transition metals, some of them are actually quite stable, and you can handle them without any complications or challenges. Think, silver and gold. Now, remember that our valence electrons are the electrons that are responsible for the chemical properties of the atoms. So the chemical properties is determined by the valence electrons. Those electrons are the electrons that are in that outer energy level, and they are the electrons that are either gained or lost in order to form bonds. On the periodic table, the elements that are in the same column, in the same group, or in the same family have the same number of valence electrons, which basically means the elements that are in the same group have very similar chemical properties. As I said earlier, you can determine the number of valence electrons by looking at the last number of the group number. So the ones digit, for those of you who remember that terminology for math, but just think of it as the last number of the group number. So group 13, for example, has 3 valence electrons. That would be your aluminum, boron, gallium, indium, all of those. Notice my example on the screen. Group 2 has the 2 valence electrons. That's my beryllium, magnesium, calcium, so forth and so on. So groups have the same number of valence, and to figure out the valence, you look at that last number of the group number. Now, my octet rule, this is the rule that basically governs how elements are going to form bonds. Atoms tend to gain or lose electrons in order to achieve a noble gas configuration. Basically, in simple terms, that just means they want to have noble gas, they want to have electrons that are the same number as the noble gas in that outer energy level. Most of the elements, considering our noble gases, have 8 valence electrons. Most of our elements are going to be gaining and losing their electrons in order to get to that octet. So we refer to 8 electrons in that outer energy level as an octet, hence the octet rule. Now, if we look at our noble gases, we'll notice that, hey, helium doesn't even have 8 electrons. It's only got 2. So it's an exception to that octet rule. Helium is very much stable with its 2 electrons. If we were to look at Bohr's model, and we remember that Bohr's model, we can only fit 2 in that first energy level. That's the reason why helium is stable with 2, because we could not fit any more electrons in that first level. So, numbers of valence electrons, nice little graphic. We are deliberately in physical science not talking about transition metals, and we also deliberately don't talk about intertransition metals because they don't follow the rules. We are focusing specifically on our representative elements. SENTITIV. I think that's spelled right. It doesn't look right, but whatever. Our representative elements are those elements that are in groups 1, 2, and 13 through 18. Those are our tall groups, and it's just they are found in the vast majority of the compounds that you actually interact with on a daily basis. Now, how do our elements form ions? Well, our elements are going to form the ions by either gaining or losing electrons. Our metals tend to lose electrons. They're going to lose electrons from that outer energy level and drop down one energy level with their electrons. This is how they form those cation ions. Remember, stupid way to remember that cats are positive is that little T, pretend it's a plus sign. Cation ions are positively perfect. But our metals are going to lose their valence electrons. So it's easy to kind of predict what charge they're going to form. Group 1 is all going to form a +1 charge because they all have 1 valence electrons to lose. So sodium with a +1 charge is just called sodium ion. Group 2 is going to form a +2 charge because they're going to lose their 2 valence electrons. So Mg +2 is magnesium ion. Group 13, jumping over to aluminum, since aluminum is the first metal in that group, aluminum is going to lose 3 valence electrons to form that +3. That is my aluminum ion. My metals in group 14, Sn and Pb, tin and lead, they can lose 4 valence electrons and form a +4 ion. So my metals lose their electrons. Well, nonmetals do the exact opposite. Now, when we're looking at our metals that are losing the electrons, a really easy way to illustrate this is with the Lewis dot diagram. Sorry, went blank on what it was called. So, unlike the Bohr's model, where we're showing all of the electrons, the Lewis dot model just is showing the symbol with the valence electrons. So, looking at calcium, I can see calcium is in group 2, therefore it has 2 valence electrons. When we are initially drawing these, we start by writing the symbol and putting 1 dot on each side of the symbol. So, for example, I'm going to play with argon. Argon in group 18 has 8 valence electrons. So, we would start by putting 1 dot above, below, and on the left and right. 1 dot on each side. Then we're going to end up doubling up. And I just realized that my lovely little picture is covering up part of the drawing. So let me move argon to the other side so that you can actually see it. There you go. So argon, we draw its symbol, and we put 1 dot per side. I always start at the top and work my way around. That's just me. Really doesn't matter. So I've got my first 4 electrons. We're going to go and add the second 4, so we pair up. So we put a second dot beside the first one, and that is how we draw an octet using the Lewis dot structure. So my metals are going to lose their electrons. They're going to lose these 2 valence electrons. They transfer out, and when they lose those electrons, they form a positive cation ion. So we quite literally take the electrons away, and we are left with the Lewis dot diagram of showing calcium with no dots. The reason we have showed the calcium ion with no dots is to illustrate the fact that it has lost its outer 2 valence electrons. Since it has lost the outer 2 valence electrons, it's going to now have a positive charge. I can do that with any element. So I'm going to pick on aluminum with its 3 electrons. So this is the aluminum atom. And the aluminum atom is going to lose its 3 valence electrons. So if I just have the symbol with a +3, that is the aluminum ion. The charge is generally written as an exponent behind the symbol. I always put the positive or negative before the number, but there's really not an explicit rule for does it have to be +3 or 3 plus. Doesn't matter. Pick one, stick with it. Now my nonmetals. Nonmetals have the exact opposite properties of my metals. So my nonmetals are going to gain the electrons. They tend to have more than 4 valence electrons. So because they tend to have more than 4 valence electrons, it's easier for them to add or gain electrons to achieve their octet. So for example, chlorine in group 17 with its 7 valence electrons, it's 1 away from being stable. It is 1 away from having that octet. So I would show chlorine with its Lewis dot diagram, and I would give it its 7 dots. And what happens is chlorine is going to steal an electron from somewhere else. So this little red dot is coming into chlorine, and we can then write it with, I probably should have left it as color-coded, but that's okay. We're going to have 1 red electron illustrating the one that came in, and the other 7 were the original ones. No, it does not matter that they've moved. I just didn't think to change colors. So that chlorine, when it gains that electron, it changes its name. It no longer is chlorine. It becomes chloride. So for most of the nonmetals, we end up dropping everything except the first syllable. So nitrogen becomes nitride. We replace everything after that first syllable with an IDE. Oxygen is the oxide ion. And all of these nonmetals are going to have that negative charge because they have stolen electrons. And electrons are negative. So if I've got too many electrons, I'm going to have a negative ion. I'm going to be an anion. It's bothering me that that dot's not where it belongs. There we go. So if we were to take our phosphorus atom, group 15, it has 5 valence electrons, and we go out and we add 3 electrons to it. I don't know why it's not clicking. There we go. So the little red dots is illustrating electrons that are brought in to that outer energy level to achieve the octet. That P, that phosphorus, now has a -3 charge. It is the phosphide ion. So the oxidation number is the charge. It is the charge of your ion. So it gives you an idea as to how many electrons an element has gained or lost. Now, when we're looking at our periodic table, there is a predictable pattern in the number of the oxidation numbers that all of our elements will form. So our elements in group 1 with that 1 valence electron will always form a +1 ion. Group 2, all of those elements form a +2. We deliberately don't talk about transition metals in physical science because they don't follow the rules. So I'm going to skip over to group 13. Group 13 with 3 valence electrons forms a +3. Group 14, it depends on if it's a metal or a nonmetal. So because they're exactly halfway there, we're exactly halfway to that octet, my metals will lose electrons to form that positive charge. My nonmetal will gain electrons to form that negative charge. Metalloids, we deliberately don't play with for physical science. Group 15 with the 5 valence electrons, it is closer to that octet than it is away from it. So it's going to fill it in and form a -3 charge. All of the elements in group 15, my nonmetals are going to form -3. Group 16, my nonmetals form a group, bad Miss Rains, a -2 charge. And group 18, my halogens form a -1 charge. My noble gases, because they have their octet, they are stable. Their oxidation state is 0. They do not gain or lose electrons. So therefore, they do not have an oxidation number or a charge that they form. I highly encourage my students to write your valence electrons and your oxidation numbers on your salmon colored periodic table. So write them above each of the groups. My valence electrons, again, is that one digit of the group number, so it matches. My oxidation number, or my charge, or my ion, is related to the valence electrons, but it will not always match the valence electrons. So group 1 is a +1, group 2 is a +2, group 13 is a +3, 14 can be either or, plus or minus 4. Again, my metals are going to be the positive, and my non-metals are going to be the negative. Group 15, again, 5 electrons. It is easier to go out and steal 3 to get that octet than it is to find home and give up 5. So group 15 forms a -3, 16 a -2, 17 forms a -1, and group 18, again, no oxidation state, no ions. Notice this is a pattern. Periodic table is all about patterns. So we are counting up to 4, and then we start counting down at group 14 with that negative charge. So let's look at a couple examples. Looking at our periodic table, beryllium, Be. Is it a metal or a non-metal? Oh, well, my staircase isn't on this image, but if we were to look at our table, we would see the staircase is here. Be is to the left of the staircase, so it's a metal. Oops. How many valence electrons does it have? Well, it's in group 2. Therefore, it has 2 valence electrons. Will it gain or lose electrons? It's going to lose, because all metals lose electrons. When it loses the electrons, it's going to lose those 2 valence and form a +2 charge, or a +2 oxidation state. So let's look at another example. Bromine. Bromine over here on the right side of the table. Again, my staircase is missing in this image, but I can easily see that Br is to the right of that staircase. Therefore, bromine is a non-metal. Bromine is in group 17. Therefore, it will have 7 valence electrons. With those 7 valence electrons, it is going to gain, it is going to go out and steal an electron. It's positive to give, it's negative to steal. So since bromine went out and stole an electron, it's going to have a -1 charge, or a -1 oxidation state. All right. Nitrogen. Nitrogen is at the top of group 15. Therefore, it is a non-metal. Remember, it's to the right of that staircase. Group 15 is going to have 5 valence electrons. With 5 valence electrons, it is more than halfway to that octet. Therefore, it's going to gain electrons. It is going to go out and steal electrons. To get to that octet, it needs 3. Because remember, our goal is to have 8, or to lose them all and get down to 0. So it's not going to lose 5. It's going to go out and steal 3 more electrons. When it finds those 3 electrons and becomes the nitride ion, it will have a, badness reigns, a -3 charge, or a -3 oxidation state. All right, aluminum. Drawing my little staircase back. Aluminum sits just under the stairs, but remember, it's an exception to that metalloid rule. Aluminum is a metal. All of the others who sit on or below the stairs are metalloids, but aluminum is a metal. Think of aluminum foil. You've seen it, you've encountered it, you know it's definitely a metal. So group 13 has 3 valence electrons. Group 13 has 3 valence electrons. Aluminum is a metal. It is only got 3 dots, 3 valence, therefore it is easier to lose those 3 electrons. It is going to give them away. It is positive to give. It is negative to steal. So when aluminum goes out and gives away 3 electrons, it will always form a +3 oxidation state. And that goes for the other metals in group 13. So that is it for today's video lesson. For our practice today, you've actually got 2 activities. One, you're using a simulation to explore stability by actually adding and removing electrons to some of our different representative elements. Then you're going to take a quiz to determine valence electrons and charges. Remember, use your periodic table. It is your master cheat sheet. Lastly, as you're closing, make certain you answer these questions in the comment section for Google Classroom. Give me an idea of anything that you might have challenges with, something that you definitely stuck today, maybe that hadn't stuck from the previous unit. That is all. If you've got any questions, definitely hop into my office hours and let me assist you with this practice.